I'm sorry for the technical difficulty, guys. You've probably been staring for a year, right? So now, stare at the black spot. This is where we left off from the previous part 1. So here we are at part 2. Stare at that black spot. Another 30 seconds. Continue to stare at that black spot. And here we go. Get prepared to notice what happens. And describe then what happened. For most people, what happens, and I hope this translates to the video screen, is they see the flag invert to red, white, and blue. Notice, when we look at this flag, what are we talking about? We're talking about the opposite colors of red, white, and blue. So what's happening is the green, yellow, and black are inhibiting the red, white, and blue. What happens then when we release the inhibition? Boom, then the red, white, and blue emerge temporarily. So the opponent process theory. Pretty cool illusion, right? Well, there's more illusions to come, but what I'm really interested in is the illusions that you find and explain to me. So the reconciliation of trichromatic and opponent process theory, right? Well, the schematic diagram shows how connections of the 3 types of cones can result in opponent process cells. So we have inhibitory neurons that are operating, but then we have the neurons that are activated. So it's a combination of the inhibitory and activation processes that cause the effect that we just saw. So, to see what's important in our world, we've involved other aspects. We've talked about sensation, but now we're kind of moving into the perception. That is, how do we then process the raw transduced sensory information? Well, some things have become very important to us, like contour exaggeration, and this occurs via lateral inhibition, right? Of cells that track contour. We have a whole array of feature detectors, and this is something that I want you to look for in your assignment that I'm especially interested in. This occurs via parallel processing, and what that means is once we have that transduced sensory information, it goes to processing centers in the brain, and these processing centers can take that signal simultaneously and begin to create a percept, which is the basic unit of perception, which will ultimately become what we, quote, see or smell or hear, right? Feature integration occurs versus serial processing, so the parallel processing happens simultaneously. Once that's completed, then processing is taking place serially, one step at a time. So we see then, if we want to take a look at a cutaway of the brain, we have the retina, which remember is transducing the electromagnetic energy and providing us with neural impulses. Notice we have a crossover effect for the most part. So usually it's, the images are reversed and upside down as a result of our lens. Now the visual area of the thalamus is pretty interesting. We're not going to talk a lot about it. This is where non-conscious processing takes place and gives us very rudimentary primary visual information that's very important for survival, right? The visual thalamus has a direct link down to the amygdala, etc., hypothalamus, and can cause immediate movement, a non-conscious movement, non-conscious reaction. Now the conscious processing is going to take place back here in the primary visual area. So as we see with the brain, as you know now, we have fast systems and then we have slower systems. And generally those relate to the non-conscious being fast and the conscious processing being slower. Now the primary visual cortex area then in the back, right, is where the feature detectors and all these other elements kind of originate and the signal moves. So, Stage 1 then, we have stimuli, right? And what are we looking at? Well, we're assessing feature maps like the line slant, right? The color, etc. At some point though, the features become integrated. And the feature integration is one of the most important aspects and one of the strangest features that we have, or one of the most complex features. Feature integration not only takes place in the aspects of visual information, but later on imagine that feature integration takes place between different modalities. So if you're watching a movie and the movie has been dubbed, it was in a foreign language and they dub it in English, you're looking and you say, oh my God, the words, that is the auditory information, doesn't match the visual information. And when we step back, to me, that's one of the most fascinating questions about our brain is how does it integrate all this different sensory information and present our experience, our perceptual experience as a whole, right? We don't ever have to say, hey, wait a minute, let me close my eyes so I can hear you better. In fact, if we close our eyes, we will hear the person worse, right? And there's been lots of demonstrations of that experimentally. What this is known as, and I know I'm a little bit off topic, but it blows my mind, this is known as the binding problem. And maybe you guys will go on to help explain the binding problem. How do all these different perceptual phenomena, these percepts, get combined to be the whole of our perceptual experience? How are they bound? The binding problem. So, people who are really interested in this image of the whole, though, right, were the Gestalt folk. And the Gestalt principles of grouping say some things just seem to be automatically, innately grouped together. And we see things that are connected as a whole based on maybe proximity or similarity or closure, good continuation, common movement, moving in the same direction, good form. These are ideas that you can use, you can explore in this assignment that's coming up, right? Among others. I'm just giving you some examples here. Another one that's not on this list might be figure and ground. Let's try this picture by Bev Doolittle. Bev Doolittle is a famous Southwest artist, and as many artists, hey Annika, how you doing? Did you come to see the ponies? Yes, we gave it away. This picture is of ponies in the snow. Big question for you guys is, how many horses are there? And notice Bev Doolittle and many artists understand these processes and are great at exploiting them. How many horses are there? The problem is that we want to differentiate figure and ground, and this is a process that happens automatically. Well, in this case, Bev Doolittle has done her artistic best to confuse our ability to determine figure from ground. This is also a very basic principle that's incorporated into war. And that is, it's a military principle called camouflage. That is a man standing in front of, let's say, foliage stands out. The man being figure, the foliage behind him being ground. In this case, camouflage is designed to confuse the perceiver and not allow the perceiver to judge the difference between figure and ground. So there's a lot of Gestalt illusions, and you might want to look for those. I do have a source for you to look for illusions. I found a pretty good website that's got a pretty significant catalog of illusions. Subjective contours. These are perceived but don't appear in the stimulus pattern. And this principle of closure, you can see what is the first figure on your left, right? What's the first figure on your left? How many people want to say a square? I love doing this in class because people say, well, it's a square. And I say, nah, not really. It's actually 4 L's in various stages of inversion. But our mind, and the Gestalt psychologist said, our mind is programmed to complete the picture due to the process of closure. So we see a triangle and a circle as well. But notice it can be more sophisticated than that. And here, this is obviously a panda, but note this shape is woefully incomplete. We fill in the blanks. How do you think that's adaptive? And I've had hunters tell me, deer hunters especially, that they say, Mark, you go hunting, you rarely see, often you will not see a complete deer. The deer's not going to stand out there and say, hey, here I am in all its full splendid glory. It's probably partially hidden behind a rock, behind a bush, etc., so that you see portions of the deer. But the idea is, if there's enough information, closure will allow us to process that as a complete animal and understand what it is. So we begin to see how these processes might be adaptive. Now, how we see whole objects, This geon to whole object, right, this is recognition by component theory. So some people suggest, right, that there are 36 simple objects, right, three-dimensional form that are labeled as geons. 6 of them are shown here, right, and these are the basic perceptual components of more complex forms, right? So this is one way to approach the problem. Now let's take an example here. There's this recognition by component theory. Obviously in set A, that's obviously an airplane, and next to it obviously a cup, a watering can. But notice that we can still detect that it's a cup if we go to the row here. This is obviously a cup, and we could say, well, yeah, the other's a watering can, although that one's maybe a little tougher. The stool's pretty easy to pick out. But notice that if we further disrupt the process or eliminate some important information, note here that we don't have any closure available on the bottom, and we don't have any indication of the handle, so this is almost impossible to recognize as a cup in its form. We have a very highly evolved visual system, right, with these perceptual components. So let's talk just a little bit about visual processing pathways. The what is identifying objects. Where is localizing the three-dimensional images in space. We need to be able to do both. We need to be able to recognize what it is, but we also need to be able to recognize where it is. Notice, for threat detection or opportunity detection, where is really probably just as critical as what. So it's a combination of those two subsystems that allow us to adapt to our environment to a greater extent. And we can see that represented in the brain. Right, and this is also for your assignment. I want you to think in terms of where does this occur in the brain. So you are going to have to do a tad of research. It's not a huge assignment in terms of writing, but it's a huge assignment in terms of research. I shouldn't say huge, not for you guys, right? So we can see that the occipital lobe, the primary visual area, is where initially the processing takes place, not counting the visual thalamus, right? And then we see the different areas that we're moving to in the brain there. So how do we see in 3D? Well, depth perception. And this is part of the where, right? Binocular vision, that is, we have two eyes, allows us to have two inputs, right, that can now be compared. And it really is a pretty straightforward mathematical calculation. So, monocular vision, then we get motion parallax, we become confused. Now, when we have monocular vision, motion can help us sort this out. Occlusion, that is having one element in front of another, right, and partially blocking or occluding the object, can give us depth information as well. The texture gradient and shadows, the position relative to the horizon. So depth perception is not just a function of binocular vision. That is, if a person has one eye, they can still perceive depth. They're just not as readily able to do it. They have some issues with that. So here's some the ways to look at binocular disparity. But since this is about illusions, I want to give you this illusion. What do you see? And I'll tell you right now, this is a dastardly object. And one of the reasons this is a dastardly object and is so confusing is it doesn't exist in the real world. This is a conceptually produced object. It is not something that exists in the real world. Kyle, do you think you're supposed to be chasing Olive? They are berserk today. I warned you. So, in looking at this, once you look at it long enough, because it doesn't exist in the real world, your feature detectors are going, wow, is it this or is it that? How many of you, it's shifting back and forth between two images? Maybe it wasn't before, but now that I've said that, it's more likely to appear that way. And now, if we really want to put a lock on it, for those of you who do not see two images, do you see the one on the left or do you see the one on the right? And now, if you look back and forth and you start glancing, this thing probably starts moving. Anyway, I've just presented a couple illusions. I didn't want to present a lot of illusions because this assignment is about you and the illusions that you produce. So what are you going to do on discussion board 4? Please, if you would, find an illusion, post it, and then describe the name of the illusion. And most illusions do have a name, right? The feature detectors involved, so that's where the research comes in. What feature detectors is this illusion playing with, if that's the case? The brain area that's involved in the processing, and we don't have to be too specific about that. You can be relatively general, right? The Gestalt process involved, if it represents a Gestalt phenomenon, and a paragraph or so explaining how it works. And that's what I'd like to see. So it's not meant to be a super intense assignment. I'm hoping that you guys find it somewhat amusing. That's my goal in this assignment, but also then that it brings a concrete example to what we're talking about in this lecturette. There's a ton of illusions available at this website, so you can check that out. There's going to be other websites as well. And then, you know, I thought as I was finishing this up, I thought, you know what? And in the next class session, after the assignment's been turned in, so you're going to post it on DB4, and that way everyone can take a look at these illusions, right? I think in our next class session, right after that, be prepared to vote on on your most favorite illusion. And let's see what we come up with, right? So, work hard, scour the illusions, you know, think about it. Present your favorite illusion, and then let's see where we go with it. So thanks, guys. Enjoy.